In today's video, we're going to talk about zeros of a polynomial, specifically factor formed polynomial, because it's not always easy to figure out the solution to a polynomial. So first, let's discuss what does it mean to find the zero of a function. The zero of a function is basically the x-intercepts of a function, because what it means is you want the y value to be zero. So y represents the f of x. So what you want is solve where f of x equals to 0 if they ask you for the zeros of the function. Zeros of a function f. So when the y value is 0, basically you're looking for these points where the y coordinate is 0. And what are those points? Those are exactly the x-intercepts. So if you're given a function, you're looking for the zeros of that function. You're basically looking to find out what are the x-intercepts. Okay, it's not always possible to figure out the solution to all types of polynomials. Polynomials, we've so far discussed only linear and quadratic, and cubic and higher degree of polynomials are not that easy to solve. If you can factor them, then you can reduce it and solve them. So here what I'm going to discuss is some idea that we already mentioned. Let's say you have two numbers multiplied by each other equal to 0. What you can say is, as we've discussed, this is the zero product. One of them has to be 0. Either the first number is 0 or the second number is 0. What if instead of multiplying two numbers, what if it was product of three numbers? And I ask you to fill in these boxes. Say three numbers multiplied by each other equal to 0. What you can say is still the same idea. One of these numbers must be 0. Either there is a 0 here, or 0 here, or 0 here. So therefore, this could be 10 times 20 times 0. Still the result is 0. It's enough to have one of the numbers 0. So if you can write a polynomial in a factor form, then what you can say is, if I have parentheses multiplied by each other, and on the other side I have 0, what I can say is one of these parentheses must be 0. The outcome, therefore, I should have a total product of the three numbers, or if it's four parentheses, the four numbers must be 0. Okay, so it's enough to one of these parentheses to be 0. Here, let's use this idea to solve, to find zeros of a polynomial with the higher degree. So let's, for example, let's assume f of x equals x minus 1 times this x minus 1 times x plus 2 squared times x minus 3. And they ask you find the zeros. Find zeros of f. First, let me explain something that is very important to know. If you're dealing with a power, if there's a power out here, in this case it's power 2, that is nothing new. This is same as thinking about it as x minus 1 times x plus 2 times x plus 2 again, because to the power 2 means you have it twice, then times x minus 3. This is the same polynomial. These two are equal. So if you say this polynomial is 0, that means the same as these products are 0. So what you can say is either x minus 1 is 0, or x plus 2 is 0, or x minus 3 is 0. This is because you do not really care about if you can say or x plus 2 is 0 again. You already have found the solution here, so it's not necessary to rewrite this x plus 2 twice. That is as long as you have an exponent outside. If there was exponent 3 here, it doesn't affect anything. You would say either this parentheses is 0 or the other one or the other one. The power is just means how many times that parentheses have been multiplied by itself. Okay, so if you want to solve this, you just set these three equations equal to 0 and figure out what are the solutions. And this is a linear equation: x equal to 1, x equal to negative 2, and x equal to 3. These three numbers, these three numbers specifically, x equal to 3, x equal to -2 and x equal to 1 are the solution to this equation. If you replace 1 into the equation, this parentheses would be 0. If you replace -2, this parentheses would be 0. If you replace 3, the other one. The same here. 1 makes this 0. -2 makes both of these 0. So it's not necessary to consider both solutions. Just need to check one of them, pick one of them. And the other one is x minus 3 equal to 0, which is x must be 3. Okay, here let's do one more example. Let's say f of x is given 2x minus 1 to the power 5, x plus 2 to the power 3, x times x. Let's put the times x here. Okay, and I ask you, what are the solutions? What are the zeros? Find zeros. Okay. Again, you can always think about this as f of x equals 2x minus 1 times 2x minus 1 times 2x minus 1 times 2x minus 1, and I'm going to write it just so you get the idea. 5 times multiply by each other, multiply by itself. X plus 2 multiply by itself 3 times. And you have times x. If this was like x to the power 2, you'd say times x times x. This would be basically the function f of x. And if you set f of x equal to 0, you say I set this equal to 0 to figure out what are the solutions. Then I should say either this is 0, or this is 0, or this is 0, since there are products. One of these guys need to be 0. Okay, so what do I get? 2x minus 1 equal to 0. Again, 2x minus 1 equal to 0, but I already wrote that. Same. I do not need to write all these 5. I already picked one representative, which is 2x minus 1 equal to 0. The other ones are the same thing. Or x plus 2 is 0. And if I say x plus 2 equal to 0, x plus 2 equal to 0, I get the same solution. Or x is 0. So if you look at the original equation, it's not necessary to deal with the exponent at all. It's just the parentheses must be equal to 0. And this x must be 0. This is x minus 0. So what are you going to get as a solution? X equals 1/2 here. X equal -2. And x equal to 0. These are the 3 solutions. Okay. But the exponents tell you some information about the solution, which is quite important if you're graphing the function. What information did they tell you? The exponent tells you here, for example, exponent 5 means you would have this parentheses 5 times. So that parentheses equal to 0 happens 5 times. 2x minus 1 equal to 0 happens 5 times. Therefore, x equal to 1/2 has shown up 5 times as a solution. So I can say multiplicity of that solution, multiplicity is the number of times that solution shows up, is 5 for the solution 1/2. How about for the solution? This m is not the slope, it's the multiplicity. So I'm going to use MULT. Multiplicity here for the solution x equal to -2 is 3 times, because I have x minus x plus 2 3 times. So I'll get that solution 3 times. X equal to 0 has multiplicity 2. And these are exactly correspond to these exponents. This is if you factored it properly and you found all the solutions. Therefore, the multiplicity tells you how many times you have that solution repeated. So the solution x equal to 1/2 shows up 5 times, x equal to -2 shows up 3 times, x equal to 0 shows up 2 times. Okay, so these exponents are useful in that case. Not always is going to be exactly the same. Here, so let me show you an example. So here, let's say you have 2x minus 4 squared times x minus 2 times x plus 3. That's the power 3. Let me change this to the power as power 1. Let's keep it as power. And again, we're looking for find the zeros. And let's say, and their multiplicity. And their multiplicity. Okay, zeros of f, that means this parenthesis is 0. So 2x minus 4 equal to 0. Or x minus 2 equal to 0. Or x plus 3 equal to 0. Right, so far it's just we're setting each parenthesis equal to 0. Whatever the solution to this equation is, it should have multiplicity 2. Multiplicity should be 2 because of this exponent. Whatever the solution to this equation is, it should have multiplicity 1. And whatever the solution to the other equation is, x plus 3, should have multiplicity 1 because of the exponents. Multiplicity 1. Let me show you equal. Because the exponent here are 1. Okay, so what is the solution to the first equation? 2x equals 4, x must be equal to 2. What is the solution to the second equation? Again, x equals to 2. Last one, x equal to -3. So what does this tells us? This tells us the solution x equal to 2 shows up twice here. And again, x equal to 2 shows up one more time here. So these two parentheses can be combined together because they give you the same solution, but it's not in the proper factor form. So what I can say is, from these two, I have a new information that x equal to 2 is a solution, is a 0. With what multiplicity? Shows up twice as a solution here, one time here, so therefore the multiplicity of that is 3. And x equal to -3 only shows up as a solution one time, so it has multiplicity 1. So this is totally fine. Okay, so sometimes the factored form is not the proper factor form, so the exponents are not going to give you exactly what you're looking for. So you have to combine the solution. In this case, each parentheses give you separate solution, but turns out that two of those solutions are the same. X equal to 2 shows up twice, then you add the multiplicities. We're going to use this multiplicity later to graph the function properly. Here, so at this point, let's assume we've done enough example on how to figure out the multiplicity. And behavior of a polynomial. So let me shift this up a bit, since we have space, and maybe the graphing. And behavior of a function, specifically for polynomial. Polynomial, f of x, for example, could be 2x to the power 4 minus 3x squared plus 3x plus 1. Something like this. We call this polynomial in descending order because the exponent starts to decline. It's from 4 to 1, and there is no exponent. That means the exponent is 0 for the variable x. So if you write a polynomial in descending order, the very first term of the polynomial, this first term with the highest degree, this is what we call it the leading term. Leading term. So assuming that the polynomials are in descending order, the first term of the polynomial is the leading term. In this case, let me ignore this n. Normally there is an n, but I'm going to stay with ax to the power n. Say this is the leading term. The degree of the polynomial, this n is called the degree of the polynomial. It's the largest one. Here, 4 was the degree of the polynomial. The coefficient up front was 2 here. In this case, the coefficient is this constant a. This is the leading coefficient. Leading coefficient. It's very important to discuss this before we jump into the end behavior, because the end behavior of a polynomial only depends on this term. It depends on the largest degree. Okay, so let's assume we have a polynomial. Let's assume we know the leading term and the leading coefficient. Based on that, we can discuss the behavior of the function. I'm going to show you the behavior of the function just based on this example. Let's assume this is our example. And we know the leading term is 2x to the power 4. Okay. What does it mean, the end behavior? The end behavior means as x gets very large, so normally they write it as x approaches to infinity. That means x is getting very large. Or let's assume x is something like 1 million, 1 billion. X is a very large number. What happens to the y value? That would be our question. Or if x is very small, that means if x is going toward negative infinity, x something like negative 1 million, then what is the behavior of y? What happens to the y? Is it y positive number? Is it 0? Is it negative number, huge negative number? Or we're going to answer that question. We're going to figure out what is the y behavior based on the given function. If you look at the given function, in this case 2x to the power 4 minus 3x squared plus 3x plus 1, if you replace something like 100 into the function and say I give you x equal to 100 and ask you what is the y value, what do you expect is 100 to the power 4, it's like 10 million. 100 squared is 1,000, so you would have 2 times 10 million minus 3,000 minus plus 300 plus 1. That 3,000 and 300, they do not have any effect on the 2 times the 10 million. 10 million is going to be very large to get affected by the other numbers. So what really decides the y value is this leading term. It's the 2x to the power 4. X to the power 4 is power 4 tells you what happens to the sign. If you put in a positive number for x to the power 4 turns out to be positive. If you replace a negative number, x to the power 4 still makes it positive. So if the exponent is even, the outcome is always positive. If you replace 100, 100 to the power 4 is a positive number. If you replace negative 100, the outcome is still a negative 100 to the power 4 is still a positive number. But what happens if you multiply it 2? 2 times that still positive. If this was negative 2, then it turns into a negative value. So this coefficient tells you what the sign at the end is. In this case, if you replace 100, since the coefficient was 2, what you get is 2 times 100 to the power 4. The y value is still positive and it's a very large number. Normally we say if x is approaching infinity, means if x is getting bigger, what happens to y value? Y value approaches it. This is when you have even exponents. Here is the graphing for the functions. So here, let's say even function we discussed here. Something like x squared. X squared to x squared. What happens? This is the even exponent. Here, this coefficient. Even exponent. That means the behavior always is positive at the end. Or always negative. How do you decide? It depends on this coefficient. On both sides, you will have positive y values. You go toward x positive infinity or negative infinity, the y value is positive. Or you go toward positive infinity and negative infinity, and the y value is negative. One of these two cases. So if the leading term is something to the power even, 3x to the power 4, 4x to the power 8. If this exponent is even, you always have these two cases. You'll have something like that or something like that. We don't really know what happens in the middle, but you know at the end, the graph would look like this parabola shape. Okay, so one of the two cases. When is it upward? When the coefficient, the leading coefficient is positive. When it's downward? When the leading coefficient is negative. Similarly, if you have something, the odd exponent, something like 2x to the power 3, you have an odd exponent, then the polynomial would have the shape of one side in the positive area, the other one is negative. If you remember x cubed, would have had this format. X to the power 5 has the same idea. Even x to the power 1, this straight line, still going positive in this direction, negative in the other direction. So if you have a leading term of odd leading term, then the end behaviors are one side is positive, the other side is negative. The blue line is when the coefficient is positive. The red line happens when the leading coefficient is. I can show you through an example. So for example, let's say f of x is given 3x to the power 5 minus 2x squared. And they ask you, what is the end behavior of this function? You don't really know what happens in the middle. I do not know what's going on here for the graph. But based on this leading term, since the leading term is 3x to the power 5, what can I expect is, since it's x to the power 5, I know it's going to be either something like that or in the opposite direction. How do I decide? I look at the leading coefficient. If it is positive, then what do I pick is this case. I say something happens in the middle. Maybe the graph looks like this, but at the end, it's gonna behave like that, like these two curves. Okay, we don't know what happens in the middle. That's what we're gonna figure out later. That's why we care about the zeros of polynomial. So what we know only is this end behavior, and only depends on this coefficient and the leading term. 3x to the power 5 in this case is the leading term. What if it was something like, do one more. For example, if it was f of x equals 2x minus 1 squared times x plus 3 times negative x minus 1. Okay. Now this is not, you cannot say the leading term is something that we already know. You do not know the leading term, so you have to figure out first what is the leading term. Because you have to distribute all these to figure out what is the leading term. But here's a shortcut for you. These constants do not make any difference in the leading term. They do not affect anything. So what do you pick is, you pick the largest term in each parentheses. Okay, this is 2 is still there, there's 2. I have x squared, and I have x here, and then there is a negative x. I multiply all these together. Sorry, this is not f of x, this is the leading term. I pick the largest term from each parentheses. Here, the largest term was 2. Here in this parentheses, the largest term was x. The other one was x again. And this last one was negative x. These are the leading term in each parentheses. If I multiply all the leading terms, what do I get is the leading term of f. So what is the leading term is 2 times negative, it will be negative 2, x to the power 4. This is the leading term. Then how is the end behavior of the polynomial? It's an even exponent, so I know it's going to be either this case or something like this. Again, you do not know what happens in the middle. But what you can say is one of these two happens. I look at the leading coefficient, it's negative, so I expect some parabola shape downward. I'm going to guess something like that. And then later on, if you figure out the zeros, you say these two are the zeros, I can guess, okay, this is how the graph looks like, probably. Not for sure, but it's possible. Okay, so we're gonna figure out later how to graph this precisely. Okay, this is the leading behavior, the end behavior, based on the leading term. You can always do this for polynomials. Now, if we know the end behavior, the question is, based on the zeros, can we graph the function more precisely? If I know these are the zeros, then can I do this and say, this is how the graph looks like properly? It has to go through all these zeros. So what we're going to discuss is zeros, or the intercepts, and what does the multiplicity do? Multiplicity was how many times you have that repeated solution. Okay, so first, let's say graph has, I've considered two cases. Here, let's say there is a zero of a function. That means there is an x-intercept for the graph. If the multiplicity is an even number for that 0, then the graph only touches the x-axis. It never crosses. It will look like something like that. Doesn't really matter which direction it goes, it never crosses. It only touches the x-axis. On the other side, if there is an odd multiplicity, these green points are, let's say, zeros of the function. In the case of odd multiplicity, the graph has to cross. So if you have a 0 with odd multiplicity, the graph will cross. If it's an even multiplicity, then the graph will touches and cross and come back. We're going to use this to fill in the gaps in between. So if I knew this is, for example, an odd multiplicity, the graph will come here and cross and say, let's say we know this one is even, and it will touch and come back. And it has to, let's say, assume this one is even again, it touches and come back again. And this one is odd, then it crosses. And it will look like that. All those even and odd multiplicities are useful to fill in the gap in the middle. So here, as an example, graph this function, f of x. And what we do is we do not want to precise exactly graph it. We're going to use the multiplicities and zeros and the end behavior. So first, let's discuss the zeros. What are the zeros? Either this parentheses is equal to 0, zeros and multiplicity, maybe I should say, and their multiplicity. Okay, so x minus 1 equal to 0, x plus 2 equal to 0, or x minus 4 equals to 0. Each parenthesis is equal to 0, and you'll get solutions x equal to 1, x equal to -2, and x equal to 4. What are their multiplicities? Multiplicity of the first solution, is coming from this parenthesis. The exponent tells you the multiplicity, so multiplicity here is 2. Second solution, x equal to 2 equal to 0, it comes from this parenthesis. The exponent here is 1, so the multiplicity is 1. And the last one is multiplicity 3. As the exponent for that parenthesis is 0, 3. Okay, I figured out the zeros and their multiplicity. How about the end behavior? How does the end behavior look like? First, I need to figure out what is the leading term. Leading term. I look at each parenthesis and I pick the largest term. I have a 3 outside. And in the first parenthesis, there is x to the power 2, x squared. In the second parenthesis, there is an x times x. It's not addition, it's multiplication. All these parentheses are multiplied by each other. And I'm going to pick the leading term in each one. In the last parenthesis, there is an x, but there is power 3, x to the power 3. And if you multiply these, you'll get 3 x squared times x times 3. You add the exponent, 2 plus 1 plus 3, 3x to the power 6. This is the leading term. And if you look at the leading term, what does the end behavior look like? Since the exponent is even, it will look like this. And just because the coefficient was positive, it's going to be the upward. So I know the graph will have this end behavior. Maybe I should choose a different color. It will look like something like this. And there would be some crossing or intersection in the middle and go back. So I do not know exactly where those points happen now. I'm going to combine it with the multiplicity and the zeros and figure out exactly the plot, how the graph looks like. So here, let's use the zeros of the polynomial. X equal to 1 is a 0, so here 1 is a 0. X equal to -2 is a 0, -2, that's a 0. And x equal to 4, let's say 4 is here, this is another 0. So the graph has to cross these 3 points, or touch these 3 points. That's the only time. You can never cross somewhere else. You cannot cross here, because then that would be a solution as well. Okay, so the only time that you touch the x-axis is through these points. And the end behavior, it should look like this. At some point, we have to reach to this curve. Okay. Multiplicity tells you if you touch or cross. So I'm going to start from the left side, for example. I continue the path of this curve. And I approach to that solution -2. Do I cross or do I touch that point only? Is I look at the solution -2. What is the multiplicity? Multiplicity is 1. If you have an odd multiplicity, graph crosses. Somehow I have to reach the other solution, so I'll go toward the other solution. Do I cross here? I look at the solution 1, x equal to 1. Multiplicity is 2. This is an even multiplicity. Therefore, I only touch that point and I come back. And then I look at solution 4 as odd multiplicity 3. So in that case, I have to cross here. And I continue to get the behavior of the graph. So what you have is now it's an approximation of how f of x looks like. Maybe you can make it more precise by picking points and figuring out exactly what are the x and y coordinates. But through the based on the multiplicity and the end behavior and the interception, the x interceptions, you can exactly figure out how the structure of the graph looks like. We can do maybe one more example just to make sure you get the idea. Here, f of x equals -2 x. Let me put an x here. -2x x plus 5 x minus 2 squared x plus 1 squared to the power 4 here, for example. Instead of squared, let's change this to the power. And we want to graph this function. Again, always figure out the zeros. You'll get either this is 0. Don't forget that. You'll have -2x equal to 0. The -2 does not do anything. It's either x equal to 0 or x plus 5 equal to 0 or x minus 2 equals to 0 and finally x plus 1 equals to 0. There are 4 terms multiplied by each other. One of them has to be 0. X equal to 0, already x is 0. X plus 5 equal to 0, x equals -5. Here x equals 2, and here x equals -1. How about their multiplicity? 0 has multiplicity of 1, this is x to the power 1. Here multiplicity is, for x equal to -5, multiplicity is 1, again exponent. Multiplicity in this case is 2, and here multiplicity is 4. Okay, how does the graph behave? The end behavior? Need to figure out the leading term. The leading term is -2x times x, this is power 1 times x squared times x to the power 4. I'm picking largest term from each parenthesis. So -2x to the power 8. What does the graph look like? How does it behave at the end? Even, so it should have a downward in both directions. And since this is -2, that's why we picked this downward case. And now I combine all these information together. You have a certain number of zeros. In this case, 4 of them. X equal to 0 was one of them. Go up. X equal to 0. X equal to -5. So here, let's say this is -5. X equal to -1. This is -1. And x equal to 2. And end behavior, we already have the end behavior. So I expect something like this. Maybe it's not good to draw these curves already, but what you expect is this curve has to go toward that -5. That's the first point that either cross or touches. So -5 has multiplicity 1. So you have to cross here. Come back toward the -1. -1 has multiplicity. -1 has multiplicity 4. At this point, you only touch that point and you come back. Let me fix this a bit. Because normally when you touch the point and come back, you should do it smoothly. Okay. X equal to 0 has multiplicity 1. I cross here. And go toward 2. At 2, the graph has multiplicity 2. So it touches and come back. And here we go toward the curve. So what we create at the end is this graph, and that graph is what you have as the graph of f of x. Okay. I hope this is clear enough. This is enough example for this subject. And I'm going to stop at this point.